How do you get your exercise in?
So I have a Tonal at home.
A Tonal? Is that the like cable thing that you attach? Okay.
It's got arms. You can turn it into a thing that can do deadlifts. You can turn the Tonal into, I think that can do bench presses.
So is it two cables into like a unit with like basically a couple of motors?
That's right. That's right. Yeah. It's so weird. You get a sense for how it works a little bit. Like it's not like picking up weights. It has kind of a linear resistance. So it's not like a band either, because a band, as you pull it back, it kind of gets harder, but it's just linear the whole time.
Interesting. So, it's like a rowing machine or an ergo.
Yeah.
Interesting.
Absolutely. But what I love about it is it measures everything.
Okay.
So
that's such a tech bro thing to say.
Yeah. But I mean, like, do you really, it's hard to know if you're improving or you just are having a good day or a bad day.
That's fair.
With the Tonal, you have so much data that you really start to get a sense of where your strength actually is. And if you haven't worked out in a while, how much it degraded and how long it's going to get to come back. So I love those graphs.
You use that as motivation?
Yeah, I think so.
Do you think the carrot or the stick, like the up or the down, motivates you more?
Definitely the up. Okay. Definitely the up. Like it's fun when you are kind of riffing and you're lifting more each week or each time. Just even if it's just by another thing. Tonal lets you do kind of these small adjustments.
Okay.
So you can go up by 1 pound. That's kind of hard to do, or at least annoying to do if you're deadlifting or something like that.
That makes sense.
Yeah, you're not gonna like put on like 1 pound at a time. You're probably gonna like go up by 5 or 10 and fill out. But with Tonal, it's very easy to go up incrementally.
That makes sense. Do you end up putting, is it like cables through arms or is it like hooks on the roof and stuff?
Yeah, it's all cables through the arms. Everything is through the arms.
Also, it's got, okay, so it's like a little unit on the ground with two kind of arms hanging out.
No, it's on the wall. It's on the wall. It looks like this when you put the arms out. So the arms go down and they also slide up and down.
Okay.
Yeah. So there's a bunch of ways to configure. You can do almost anything except for some reason the back squat. They do not let you do a back squat, like where you have a bar on your back. You can have a bar on the front, but not the back.
So you could totally do the exercise and just not tell them.
You could just not tell them, but then they wouldn't track it. I'm disincentivized. They will let you do a front squat.
Do you think there's a reason for that?
I don't know, but it's got to be a safety thing.
It must be.
It's got to be a safety thing. But I can't think of how it's like, I don't know. Like, I guess you got to think of how the failure modes work when people are lifting and how they get uncomfortable or whatever. Maybe somebody got hurt while they were testing and they were just like, all right, screw that one just because somebody got hurt.
Do you reckon they've done a DFMEA on like the human body in different positions to work that out? So
a DFMEA designed for manufacturing?
No, it's basically a failure analysis. God, I'm going to need to It's design, failure mode, and effect analysis. But basically what the activity looks like is you go through, typically you sit down with someone from reliability or safety or whatever department it is in that company who'll go through with you and basically poke and say, okay, and if this wire breaks, like what will happen?
Oh, I see.
And you say that, like the whatever, the whole unit will shut down and we'll lose engine power. Like it's typical in aircraft and, of course we do it in automotive and stuff too. So you lose engine power. And okay, so what's the follow-on effect of that? Well, you're allowed to lose one engine and over here and one engine over here because you can still balance for the multi-rotors, for example.
Yeah.
And so you use this type of analysis to work out how reliable everything needs to be. And you do it down at the component level. So in electronics, one of the most annoying tasks that I cannot wait to automate with Adapile is we had like multi-thousand row spreadsheets to go through and say for each pin in a design, if it shorted to any of the adjacent pins or ground, what would happen?
Oh, interesting.
Yep.
Oh, huh. What? And this happens just in production. Like people will have a trace cross or something fall over a wire. Is that like common?
It's more typical. So have you ever heard of tin whiskers?
No, tin whiskers. That's that's when like tin kind of like grows, like it's almost like metal grows off metal.
Right, exactly. Yeah. It's crazy. Like the crystal structure it forms is just like a hair. It's like a whisker. And I believe they can grow up to like 10 millimeters long in some cases.
Yeah.
And this is like in space where there's no atmosphere to disturb them and all sorts of stuff.
Yeah.
But it means that one, you can't use tin-plated electronics in space, or you typically don't. It's a bad idea because you end up with these long whiskers that will just sort of branch out and poke something adjacent. And for DFMEA's sake, what it means is like, I don't know, a tin whisker can be pretty thin. So if it's a high current thing, you might not care because it'll just blow up your tiny little fuse and continue unbeknownst to anyone. But if you have a signal, for example, it could bias something in the wrong direction. It could falsely tell you something about that signal, that you're an overcurrent situation or whatever. And you might, for example, blow a pyro and disconnect a pack, destroy a product, basically speaking, because you don't know. So typically with a DFMEA, there's two things you're looking for. It's like, what would happen? And then is there a way we can detect this failure mode? And if there's a way you can detect it, you can kind of subvert some of the worst effects and continue. And therefore that's, you space out your redundancy. You don't put things adjacent to one another such that if it's either tin whiskers or crud, basically, some FOD getting in there, some debris.
Very interesting. So to automate this process of DFMEA, you would kind of like run some kind of static analysis that would test shorting pins together and make sure there's some kind of failure protection?
Ideally, or detectability, as I said. Like that can be your outcome kind of mode.
I see. Very cool. I guess so getting back to the tonal, the equivalent would be, okay, what kind of ways will a human fail? Like if you're doing a bench press and it's stuck there and kind of choking you out, what does that look like?
Design failure mode and effects analysis. What's the effect of pulling your shoulders back? It doesn't sound great. That might be it, really.
Yeah. One thing I do like about it, this is like a long tonal commercial, but
sponsored by.
Yeah, exactly. But when you're pushing it up and the bar kind of goes
askew.
Asymmetric, somehow askew, it'll stop. It'll turn off the weight.
Oh, so, yeah, nice.
And it's got like buttons to turn off the weight, but sometimes, if you're really pushing, maybe you can't do it or whatever. You can't lift your thumb to press the button. So pretty cool.
I imagine they've probably got some like max acceleration type safety as well. So if you quickly like let go and jerk, it probably stops tugging on you pretty quickly.
Yep, absolutely.
Oh, it's so interesting.
So jumping back to the new Autopile office, everybody's going to work out together. What other like routines, are kind of are make up a good hardware company culture, I guess.
Yeah. For us, because we're really a software company. We're just a hardware company at heart.
We're all in disguise.
We're all in disguise.
Software companies disguised as hardware companies.
Roughly speaking. So institute Friday afternoon as design your project things. And so for me, that's a project called the Bikey Wagon, which is a trailer for my bike. I cycle as much as I can, and I want to bring stuff with me sometimes. And the hills in San Francisco can be pretty rough.
Unforgiving.
Unforgiving is the nicest way to describe it. And so if I want to bring, I don't know, an esky or a barbecue to the park with me on a Friday afternoon to have a barbie with my mates, I just like have to drive today.
Right.
But I want to be able to put that behind my bike, have two driven wheels basically, and a load cell in the coupling to my bicycle. And so it fully compensates for the weight. It's a weightless trailer.
Oh, nice. A weightless trailer. I really like that. Okay, so this is kind of like an e-bike trailer.
Exactly. That's it.
Okay. Very cool. How's it going? How far is it along?
So there's like a top level design element to it, which I've done. This Friday comes to the actual board, and I'm going to put basically two motor drivers from a previous sort of Friday style project we've done called the Spin, which is a little servo drive. So take those motor drivers, put two of them on this board, dramatically increase the power, put an ESP32 on there and the load cell amp, and then order that board.
That's super interesting. So the ESP must be taking the weight, or maybe you calibrate it. Oh, maybe does the phone... I'll let you explain. What does the ESP do?
Well, it does three things. Firstly, it drives each of the motors, so those two.
Right.
And are you familiar with like an FOC motor control?
I don't think so.
Roughly speaking, how brushless motor control works is that you have to determine the rotor position, and you can do that either with a sensor or watching the electrical signals really closely from the motor, which is a little less accurate unless it's spinning quickly. So you determine the rotor position with respect to each of the magnets. You can kind of just imagine one pole of, north-south permanent magnet, and then three electromagnets where you sort of north-south them as necessary to sort of drag that permanent magnet around. And then what your objective is always to keep the electromagnet field 90 degrees off from the permanent magnet because that gets the most torque. And so you're doing this 20,000 times a second on the microcontroller for each motor and switching the FETs to sort of generate that electromagnetic field as you pull that motor around. So 2 of those motor controls, like general like settings to your phone type of thing, and then the control loop from the load cell, which is just measuring how much I'm tugging the wagon, and it's just simple PID loop. So
interesting. So how much you're tugging the wagon is
the complete control signal.
Gotcha.
Yep.
You don't need to know the weight of the wagon. You just know how much. By the way, wagon, like trailer.
Yeah.
Also, is bikey a common term as well? Or that one, it could go. I could go either way.
We've tried to give all these Friday the premise of the Friday projects is light, fun, get everyone to actually try out a pile and build something in it that they want.
Right.
And so we try to make it like stupid and fun, basically. And so every one of the projects just has a dumb name.
Yeah, makes sense. And I feel like people maybe conventionally would put a lot of effort into like naming and working on a project because it's a really big effort. But with Autopile, I think both of us feel that electronics as code kind of speed up how quickly you can develop these things. You have so many reusable modules. It's not as big of a deal to like put that much weight into the project. It's not going to be, maybe it's a month project now because the products are early, but in the future, these will be like week or day projects or something.
Oh, it's a month project because the firmware's like become the hard bit again, which is
that's right.
Fantastic. That's like our entire objective, right?
That's our objective is people can say, yay, we only need to fix firmware.
Yep. Thank God. Have you tried Embassy and Rust?
I have not.
Okay, so I'm yet to try it myself, so I won't talk too much about it. But the gist of it is it's a async Rust framework for microcontrollers, including all the regular suspects: STM32, ESP32, the NRF family of wireless NICs, and the RP2040. And you can just write sort of async code, task-oriented code like you would in Python analogously or in TypeScript or JavaScript as well, have promises come back, and run almost a really lightweight RTOS in Rust.
Nice.
And it's kind of like a next level Arduino. So I can't wait to get my teeth into it.
Absolutely. I have done a little bit of Rust. It still intimidates me a little bit.
Yep.
What's your stack ranking of like, I would love to write in this because there's MicroPython. There's I don't think it's super robust. I could be wrong, but there's a micro JavaScript kind of thing.
Oh yeah.
There's I guess Zig is very popular today. I don't know if it's popular for embedded.
Interesting.
I'm not sure.
Yeah, I've never seen Zig used in embedded actually.
Yeah.
I'm sure it's doable, but it's not my flavor. Look, I'm primarily a Python dev, so I'm biased towards MicroPython. But I've actually worked at a company in the past that put embedded MicroPython into therapeutics devices.
Oh, wow.
They certified MicroPython.
Oh, no way. So you can use MicroPython for medical devices or like
this was like a diagnostic equipment. So it wasn't like real-time critical, if it's it needed to fail in known ways, for example.
Yeah.
But the reason they did this, and this is incredible, like I love this mentality. So the reason they did this is because they were developing a bunch of image algorithms to examine slides, let's say. Won't get into the details of that for IP reasons, but basically what it meant is they could develop all of this software on the computer using a regular Python stack and general purpose Python, OpenCV, and then build against MicroPython on the microcontroller and run the exact same validated code after having just develop the whole thing.
That's crazy. So they were writing Python with OpenCV, Open Computer Vision, and then moved that to a microcontroller.
Yes.
Wow.
Incredible.
That's crazy. I mean, this must have been I don't know if you could say, but this must have been a powerful microcontroller too, if it's running OpenCV.
Yeah. So there's a project, I think it's OpenMV, I believe it's called, that brought basically the same OpenCV like environment to microcontrollers.
Oh,
so they got to
cool.
leverage that with the MicroPython and just develop on a computer, which is incredible. It's so portable. And so mimicking that in MicroPython for any device that doesn't need to be real time is 100% the way to go, in my opinion.
Oh my gosh, I love it. We're going to turn into a firmware podcast, you know.
If we're not careful.
It's the next thing. That's how I feel kind of building a product for building electronics with code is once people do one thing, they want to move on to the next thing. And there are a lot of next things.
There's a lot of next things.
After you design a board, after you design a schematic, you have the PCB. Yep. After you do the PCB, you have the ordering. And ordering is kind of, I mean, it's not too hard, but it is kind of a thing where you got to know some things. And then you have the firmware. And then I don't know what comes after that.
Well, then you actually have to sell your product.
Oh, right.
Oh, man.
The part where you sell firmware. Yeah. Oh, there's mechanical too. That's like a whole thing. So the problems just keep coming in hardware.
Well, yeah. I mean, if you love hardware, it's not too terrible because, I mean, today for the say it's an enclosure, like something relatively simple need. You no longer need like even soft tooling to do some decent volume production. You can use SLS and 3D print stuff on like hundreds to thousands, like low thousands of volume, cost competitively with making full.
Absolutely.
Yeah.
I've seen a couple of products now that I've purchased that are best in class that are 3D printed. I have a MetaQuest Pro.
Okay.
And I wanted to get I wanted to play some gun games, but I wanted to win. Mm-hmm. And when you're holding the controllers like this, you don't have as much control.
Yeah.
So I got like a 3D gun,
like a frame,
to put the holsters in.
Yep.
Which made me slightly better. But everything was 3D printed, and it was 3D printed to fit a pretty weird shape. The Quest controllers are a really weird shape, but it fit in perfectly. You shove the thing through, and it's totally sturdy.
It's completely geometry agnostic. It can do anything it likes.
Yep.
Yeah.
Yep.
So now that you can do that, you can like mid-level production PCBs, even in some Western manufacturers, but like typically, you know, your usual suspects, JLC and PCBWay and all those. Right. You basically have like simple consumer gadgets done for like totally reasonable prices that are accessible to regular people. And I think that's cool.
Right. No, absolutely. It's funny because I talk to people and they say, who will want to build electronics if it's easy? Do you really have new people building electronics if it's easy? And I think the answer is yes. Who doesn't want to build something in the physical world, right? Yeah. But a lot of people say that, like, shouldn't hardware companies be the only people building hardware? And it's like, I really think it should be more accessible, and then you'll see more products. And so there's this cost for the R&D of a device. And I think, like, basically the bare minimum has got to be like, I don't know, $50,000 if you include labor to get anything out there. And that's a very low estimate. Yeah. I think for like a product that goes to production, it's closer to like 500,000 or something like that. So what happens when that gets lowered? Will people buy more or create more electronics?
Yeah, I think, did you come across the company Micronics?
I don't think so. So Micronics, what do they do?
It's topical because they just got acquired by Formlabs. But
nice.
I believe it was University of Wisconsin. I met them at Open Source this year.
Oh,
and
nice.
I've been following them for a little bit because these kids are absolute geniuses. So the Micronics 3D printer was going to be the world's first SLS machine, available for about $3,500, about a third of the cost of any other manufacturer. So SLS is obviously the powder sintering process. You have a bed of nylon powder and you run a laser through it. And that way you kind of got free support material of the unstuck together powder.
Right.
And you melt together the part you want.
Yeah.
And so they'd done some absolutely genius things. They'd put the powder storage beneath the printing bed. And so as you sort of took out from underneath and put the powder on top, you could lower the bed and there would obviously be the right amount of room to sort of shuffle this around. So it was a tiny little box. And they'd built their own optical electronics because they were just way too expensive. So they implemented PID controls in analog hardware rather than trying to do the digital controls at megahertz kind of frequency, which is like actually really hard. So credit to them, incredible development. They did it in about a year and with only sort of bootstrap fundings from their friends and family. So it gives you an order of magnitude. I don't know how much they raised, but call it $100,000.
Yep.
So that's like seriously hardcore development to do with these two guys. And, credit to them, incredible work. They met the Formlabs CEO at open source, and they got acquired like 2 weeks later.
And that was this year.
That was this year.
Wow. I bet that's going to lead to some really cool innovations with Formlabs. Now, Formlabs, you can order 3D prints from them. Is that what they do? Or do they build machines?
They build machines.
Gotcha.
Yeah.
Okay.
So they do what's SLA, so stereolithography. It's a process. You have a bath of resin and you shine a laser into that resin, and where the laser hits, it'll harden. And so you kind of pull an object out of a goop, which is incredible.
And all of these are better than 3D printing where you kind of have the nozzle and it's dropping. That's FDM.
Exactly.
All of these are a little bit better because you don't have to print support structures, so they don't have these kind of like ugly juts coming out of it.
Yep.
Yeah.
And unlike FDM, where the layer direction impacts the strength of the part pretty significantly,
right,
and you're quite limited in material choice, both of them have a pretty decent width of really impressive materials that you get to use, and they're typically pretty homogeneous.
Yeah.
So you don't need to worry, and isotropic, so you don't need to worry about the strength in different directions too much. It's a tiny variations compared to enormous ones.
That's right. Some people doing FDM will, you'll have something that looks really simple to print, like kind of like a box shape, but then they're like, we really want it to be strong in this direction. So they'll print support material and the whole thing will be like at an angle just to improve the strength with FDM. But you don't need to worry about any of that with SLS or what's the other technique?
SLA. Stereolithography.
Right. Yeah.
It's incredible. Cool. When you say you want to print something today, do you mean 2D or 3D?
Good point. I think most of the time when I want to print something, it's something 3D.
Yep.
Yeah. That's crazy.
I got my first 2D printer in years. Just what, Friday, I want to say. And it's printing to me has meant, I would say 3D for probably a good part of 6 years now.
Yeah.
It's incredible world we live in.
Yeah, you don't need to print paper. I can't really think of why I've needed to print paper. The last time I printed paper was for this podcast, but like everything else is DocuSign. Like there is no need to have any paper. Hey everyone, thanks for listening to this episode of electronics.dev. Next week we have the CEO of JITX on. JITX is a major electronics as code platform, so we're very excited for that. Be sure to subscribe if you want to know when that comes out. Thanks for listening.